Okay, here goes nothing. I realize this is going to be a little less than ideal just because you won't be able to ask questions in the moment, but hopefully I can provide a little clarification, and my hope is that this kind of helps you have a strategy that you can use while you're kind of playing with the fractions. So these right here are called fraction bars, and the basic premise is that each one is a whole unit long, and then it's divided into the various fractions by physical length. So for example, one whole is made up of 2 1/2 pieces, or 3 1/3 pieces, and so on. So one advantage is it lets you see really easily certain ones that are comparable. So for example, if I remove the odd ones for a moment, let me just slide, I've got some other stuff over to the side. I believe what I gave you is 2 full sets. You'll see why in just a moment. But if I remove the odd ones, oops, I had that out of order. Move the 9th, move the 11th. And if I bunch these up, we'll notice that they all share this middle line. You can't see that at all. You'll notice that they all share that middle line in common. Okay, and so we'd be able to see that as equivalent fractions, it is the same to say that I have a half of something, or that I have 2/4 of something, or that I have 3/6 of something, or 4/8, or 5/10, or 6/12. So we get this idea that we can scale up how many divisions we have, and as long as we're representing the same amount, they are equivalent. So we can start to see certain combinations that go together. Similarly, if I were to take out this 1/6 in the middle, we would see that it's the same to say that I have 1/4 as it is that I have 2/8. Or if I have 3/4, 1, 2, 3/4, then that would be the same as 6/8. 1, 2, 3, 4, 5, 6. One thing that you can think about with those equivalent fractions is it comes down to whether we're dividing or multiplying both the numerator and the denominator together by the same value. So for example, in the one we just talked about, we recognize that 3/4 and 6/8 represent the same distance. And if you think about those two fractions, you could think about, hey, I am multiplying by 2 on the top, I am multiplying by 2 on the bottom, and because I'm doing the same thing to top and bottom, I have an equivalent fraction. So that's just kind of something that you can have in the background. You can use these as kind of keep track of what you've got. What I want to take a moment now is I want to take a look at adding, subtracting, multiplying, and dividing, just to get some basics, and I'll try to do a representation with both the bars as well as the fraction just the straight arithmetic. Okay, so for example, suppose I gave you, we'll just start with this. Suppose I gave you 3/5 plus 4/5. Okay, so if we think about 3/5 plus 4/5, you may already have an idea, but I just want to highlight what this would look like using the fraction bars. I can take my first fraction bar, and all I'm going to do is, just to make it easier, I'm just going to go ahead and fold it. It's just paper. And so right there, I've got a bar that represents 3/5 because there are 3, 1, 2, 3, 4, or 1, 2, 3 of the 5 pieces. And then I'm going to take my other bar of 5, and I need 4 of them, so I'm just going to fold 1 over, which means that if I combine these together, then I would have a piece that looks like this. So then the question becomes, what is this equivalent to? And you can look at it 2 ways. One, right away you can probably just count 1, 2, 3, 4, 5, 6, 7. I know that I'm going to have 7/5 in total. And you might also be able to think about it in terms of, hey, I guess I should put the bar there. If I imagine what that whole 1 is, okay, then these first 5 I can group as one whole number or one whole bar, and then that leaves me 2 left over. So this is the same as 1 2/5. Okay? That means that if I was going in reverse and I had given you the 1 2/5 and you were trying to write it as, say, this improper fraction, you would take the mixed number and you would say, hey, that 1 in front as a whole, if I want to write that with a denominator of 5, then I would need to have 5/5. Because 5/5, 1, 2, 3, 4, 5 pieces of a 1/5 gives me the 1, and that's being added to the fraction piece at the end, and I would get 7/5. So you can kind of go back and forth doing that. Obviously this was a very simple problem. You probably remember from the get-go that, hey, if your denominator is the same, then that means that you can add the numerator straight across. But in case you weren't sure or wanted a strategy, you can use those. Now, let's play around with this a little bit more. Let's go with, let's try, let's do 2/3 plus, actually, let's go ahead and do minus. Let's go 2/3 minus 1/12. Okay, so we've got 2/3 minus 1/12. So I'm going to do similar to what we did before. I'm going to find the third bar, which I've got one here, and I need to start with 2/3. So I'm going to go ahead and just fold this over, and I'm now going to have 2/3. And then I need a 1/12. So I'm going to come over here, and this is going to be a little cumbersome. I want you to ignore all this hidden paper here that doesn't have any numbers on there. I've got the 1/12. Now where this is different is I'm subtracting. That's just a smudge. In fact, let's just rewrite it. Let's go 2/3 minus 1/12. And because I'm subtracting, that means I'm getting smaller. So I can imagine kind of putting my 1/12 right there. So that means I'm now interested in this distance right here, whatever that may be. And it gets a little trickier because I know the thirds won't work, because if I count in terms of thirds, this piece right here isn't a value for a third. So generally speaking, you need to go with whatever your smallest value is. So I'm going to come over and I'm going to grab my other 12th. Where did it go? There we go. And I'm going to ask myself, how many 12s do I need to fill in this gap? Okay, so I'm starting right here. And so I need 1, 2, 3, 4, 5, 6, 7 12s to complete that distance. Okay, so knowing that, we would then have an answer of 7 12s. Now to try to think about it a different way, I've got different denominators. Well, if I want different denominators and I want to add or subtract, I need to make them the same. So these 2/3 right here, I want to have a denominator of 12. If I want a denominator of 12, then what do I need to do to turn the 3 into the 12? I need to multiply or times by 4. Whatever I do to the bottom, I need to do to the top. So that means that that 2/3 is equivalent to saying 8/12. So now my problem, instead of 2/3 minus 1/12, would become 8/12 minus 1/12. And now that I have the same denominator, number on the bottom, that stays the same. and then I just subtract the numerators. 8 take away 1 gives me 7. So again, you can use the algebraic approach where we're just manipulating the values, and you can also kind of take part with the fraction bars. Okay? One more, sometimes it's not as nice to do this. So suppose I gave you 1/3 plus 1/4. Now this problem seems like it wouldn't be too bad. You start with your third. Okay, we got our third right there. And then I'm gonna take a fourth over here. There we go. This takes me a moment to find one. And I can take a fourth and I can place it here. But then the challenge becomes, well, now what do I measure the total with? Because obviously thirds won't work, because I would go a third and then I'd be too long. And fourths don't work because I'd have a fourth, I'd have a second fourth, but then I'd be missing a little bit. We can even verify that with the other fourth ticket. Excuse me. So like if we looked right here, here's my first fourth, here's my second fourth, so I know I'm bigger than a half, but I gotta go a little bit, oh, can't see that. So again, here's my first fourth, here's my second fourth, so I know my answer is a little bit bigger than 1/2, 2/4, but I don't quite have a measurement for there. So what do? We think about getting what's called the least common denominator. So I need to think about a number. Remember before when we multiplied the 3 by 4 to get 12, and then that way we had the same denominator with both 12? I want the same denominator. In this particular problem, I can't just multiply one value, but I have to multiply both. So I'm actually also going to have a denominator of 12. And so what's going to happen is I'm going to take the 1/3, and I'm going to multiply top and bottom by 4, and I'm going to get 4/12. And then I'm going to take the 1/4, and in order to get a denominator of 12, I need to multiply by 3, top and bottom, and so I'm going to get 7/12. And so putting that together, 3, my mind's a step ahead. 1 times 3 gives me 3. And so what that means is this 1/3 plus 1/4 is the same as 4/12 plus 3/12, or by a fluky coincidence, is also equal to 7/12. And so we get this idea that we can change both denominators to get what's in common to both. Okay, and we can double check this. Sure enough, 1, 2, 3, 4, 5, 6, 7. Okay? Now, if you were doing this with mixed numbers, it would just be as simple as keeping track of the fraction pieces as well as the whole number piece. So if I had a very similar problem and I gave you 1 and 1/3 plus 5 and 1/4, well, you can combine the whole number pieces together. 1 plus 5, and we know that that is 6, and then 1/3 and 1/4, which we just did, and we know that to be 7/12, and you would have your combined answer of 6 and 7/12. So you can just group them together separately in a fashion just like that. Okay? I'm going to pause the video, and then I'm going to take a moment to talk about multiplying and dividing.